Okay, for now, let's conclude with some brief introduction to projections of extremes in CMIP6 suite of models, which are being reported in AR6, synthesized into AR6, the assessment report 6, which is beginning to trickle out now. So they have added a new thing called agricultural and ecological drought. So depending on the affected biome, a period with abnormal soil moisture deficit, which results from combined shortage of precipitation and excess evapotranspiration, and during the growing season impinges on crop production or ecosystem function in general. Observed changes in meteorological droughts, precipitation deficits, and hydrological droughts, stream flow deficits, are distinct from those in agricultural and ecological droughts. So those are the three typical droughts we worry about. As soon as the precipitation that falls is less than what is climatologically expected, depending on whether it's 5%, 10%, 20%, it can be called a meteorological drought. And hydrological drought is when the rainfall results in deficits of stream flow. And that's different than agricultural and ecological drought, which can be much more important for food security and biodiversity and feedbacks, as well as wildfires and of course water resources as well. So this is a nice synthesis figure, which is slightly done differently than AR5 in terms of showing observed changes. So synthesis of assessment of observed changes in hot extremes and confidence in human contribution to the observed changes in the world's regions. So they are split into all these continents and subdivided into different regions within the continent. So Western North America, Central North America, Eastern North America, and so on. So North America, Central America, South America, small islands, Europe, Africa, Australasia, small islands, South Asia. So Asia is split into South Asia, Eastern Central Asia, Tibet, and so on and so forth. The color schemes here for the type of observed changes in hot extremes are increases, so number of regions, decreases, low agreement in the type of change. So there are two regions here, for example, and limited data and or literature to conclude, and there are two regions here in Central Africa and Southern South Africa. Okay, so let's just focus on this region then. Over South Asia, which includes the Indian subcontinent, Nepal, Bangladesh, Pakistan, parts of other Burma, and so on and so forth. You can see that it's guaranteed that there has been increase. So these are observed changes. Okay, so there have been increases in hot extremes, but the confidence is also high here. So you have to also look at confidence in human contributions to the observed changes. So here it is called attribution. So you have detected, and there is a detectable change in the hot extremes. It's defined as 95th percentile or cumulative days exceeding temperature and exceedances and so on and so forth. You can look up the exact definition, but I'm just going to leave it there. So the confidence can be high, medium, or low, or low can be due to limited agreement between observations, or low due to limited evidence. So this is attribution exercises. So you do attribution exercises typically based on models, and one has to be careful in heat waves because you can look at whether the probability of the heat extreme was changed or the amplitude of the heat extreme was changed, and you can get different answers. For example, the 2010 Russian heat wave, the probability was not changed, but the amplitude of the heat wave was much higher than what would be expected under natural variability. So the human contribution came in terms of the amplitude. So these are tricky things to deconvolve. Nonetheless, the South Asian region has been experiencing hot extremes, and we can say that with high confidence that this has human contribution. If we move to now synthesis of assessment of observed change in heavy precipitation, here they are looking at accumulated rainfall over 5 days and 10 days and not the 95th percentile type of thing for each day. So it's still accumulated and high percentiles. So confidence in human contribution to observed changes in the world's regions. So again, zooming into South Asian region, you can see that there is have been increases in heavy precipitation in the observed record, but you can see that the confidence in attributing it to human contribution is limited because of agreement. And this is a good thing to keep in mind, because this relates to what we said before in terms of multi-decadal modes in the monsoon and potentially its relation to North Atlantic, Pacific, and the Indian Oceans, as well as multi-decadal variations in the extremes themselves. So if you look at the last 50 years, we see increases in extremes as defined as greater than 100 millimeter per day, 120 or 150 millimeter per day, especially over the core monsoon zone. But this is still within the realm of natural variability, because there have been decades in the past where there was elevated frequency of extreme events. And also there is an increase in spatial variability, which also makes attribution harder. And there is a trend over 50 to 60 years, last 50 to 60 years, where we said mean seasonal rainfall has decreased by about 10% for the Indian monsoon. And this also means that global warming may be just modulating the natural variability. So maybe a 20 to 30 year cycle is becoming 50 to 60 year cycle. This will definitely be true if the monsoon is indeed recovering and remains in the higher multi-decadal phase for the next 10, 20, 30 years. Does that mean extremes will change, or will the extremes continue to show an increase? So that again goes back to understanding the scaling in terms of how precipitation efficiency, vertical motion, or the dynamics and thermodynamics, or the saturation vapor pressure with temperature are changing. So warming confidence is high. So then is the warming getting out of the natural multi-decadal variability? If not, even with the trend in temperature, will the rainfall, mean and extremes remain within the multi-decadal mode of monsoon variability? You can see that it becomes quite complicated. But these kind of analysis are also done using annual mean temperature change. So this is observed change per degree centigrade of warming from the past in annual mean temperature. So the distribution always produces this nice cooling here, which is potentially related to the change in the Atlantic meridional overturning circulation or the global conveyor belt. But people have also invoked other forcings, radiative forcings for this cooling here. But you can see that simulated changes are similar to the observed distribution, but the polar amplification is maybe stronger, and this warming whole is much weaker than observed here. Keeping that in mind, if you look at simulated changes at 1.5 degrees C global warming, 2 degrees C warming, and 4 degrees C warming, the polar amplification gets stronger and stronger, but the warming over rest of the world also keeps going up, including the oceans. There are serious implications of how the warming in the eastern Pacific will affect global warming itself, because this is the region where ocean is able to take up a lot of heat, and the east-west sea surface temperature gradient also impacts mean circulation, ocean heat uptake, and so on and so forth. So given this distribution of warming, you have to then you can see that now over with warming, the polar amplification over the Antarctic also begins to appear, which has not happened so far. You can see that there is either no data or it's hard to see a polar amplification despite this amplified warming here. Okay, so at least the models say that with increased warming, the polar amplification or Antarctica will also begin to manifest itself. Converting that into precipitation, so this is just looking at annual mean precipitation change relative to 1850 to 1900. So precipitation is projected to increase over high latitudes, equatorial Pacific and parts of the monsoon regions, but decrease over parts of the subtropics and in limited areas of the subtropics. So subtropics are the evaporative latitudes. You expect them to export moisture to the rainy bands, especially when rainy bands are getting more intense. But the story is much more complicated than that in terms of scaling per degree warming, how much additional rainfall you get. That's still more complicated. So 1.5 degrees C warming, 2 degrees C warming, and 4 degrees C warming, and you can see that the monsoon domain here remains positive in all cases and gets quite intense here in terms of percentage change with 4 degrees C warming, which again has to be understood in terms of the model biases in dry terrestrial rainfall bias, biases in extremes and cumulative rainfall days, cumulative dry days, and so on, which we looked at with convective parameterizations. But in general, you expect that ocean will warm slower than land because of heat capacity differences. That would favor a land-ocean thermal contrast, which would drive stronger monsoonal circulation and intense monsoon rainfall. But you also have to consider aerosols, which remain highly uncertain, and of course pollution, direct, indirect impacts as well. So looking at extremes, heavy precipitation over land, 10-year events. So this is the observed frequency, 1850 to 1900. In the present, it went probably from once in 10 years to 1.3 times. With 1.5 degrees C, it'll happen 1.5 with a range 1.7 and 2.7. So the quintessential loading of the dice, where the climate change or global warming will begin to make certain events more frequent. When you throw a dice, you expect all numbers to be showing up equally, probably in a random number of throws, but when you load the dice, you can make some numbers appear more frequently, which is what global warming is expected to do. And in terms of intensity increases, you can see that the observed warming has 6.70% warmer on global average, whereas with 1.5 to 4.4 degree warming, you expect the intensity to increase continuously. Okay, and the range here is much smaller than the increase. Similarly, agricultural and ecological droughts in drying regions. So 1850 to 1900, the events that occurred once occurred 1.7 times with 1 degree C warming, and expected to increase 3 to 4 times with 4 degrees C warming. So 10-year events on the dry side, remembering the definition of agriculture and ecological droughts are based on soil moisture deficiencies. Excuse me. And the intensity increase in terms of standard deviations. Very humid weather here in Mumbai, and I always get dry throat if I don't hydrate myself. Drinking coffee is not good anyways for hydration. Okay, so let's look at one example of a CMIP6 analysis where dynamics and thermodynamics were explored by doing moisture budgets. So this is the mean moisture budget looking at precipitation, evaporation, and moisture transports with the residual that cannot be resolved. And the quantities are split into climatological, zonal mean, and stationary eddies, which becomes very relevant for monsoon trough or the mid-latitude storm tracks and so on. So then there is a transient variation x prime, which gives you moisture transport terms split this way, and different models with some high resolution forced atmospheric model experiments are compared here with historical runs and data. And the main point I would make is that models differ in these kind of moisture budget details of climatological, zonal mean, stationary eddies, and transient variations, which is consistent with the dynamics, thermodynamics, precipitation efficiency, convective parameterizations, and so on, because there is a feedback from the convective parameterization converting into rainfall versus moisture demand instabilities and so on. So what is the point of showing this? Basically that when we look at such details, you are better able to resolve the details of where models differ or agree or disagree with observations or reanalysis in terms of the dynamics, large-scale circulation versus local convective circulation, large-scale moisture transports versus local vertical transports of moisture converting to precipitation efficiency and so on. So to improve models, these kind of diagnostics become very important, as well as to understand where the biases come from when you look at maritime rainfall versus continental rainfall and so on. So those are very useful for advancing process understandings so that models can be improved, and predictive and projection understandings and biases can be advanced as well, so that we have a better handle on the model uncertainties in historical simulations and convert that to understanding of uncertainties in future projections. Okay, so that's just an example. I kind of run through these things because they are just meant for introduction. I give the reference in each case, which you can go and look up for further details. If you're a modeler, you're probably going to do many of these kinds of diagnostics, and you know how they help in understanding the models better and the model details better in terms of dynamics, thermodynamics, and comparison with observations, including orographic rains, rainfall over land, or rainfall over the oceans, what controls the moist static energy instability, scape, and so on and so forth, atmospheric instability versus surface controls, SST forcing, and so on and so forth. Okay, coupling strength, etc. Lots of details. I'm throwing these words. If you don't understand, don't worry, but if you understand, then you know what I'm saying. Okay, let's leave it here.